Lab 1 starts this week. Some of you guys already started it yesterday, and I'm sorry, computer lab I heard was completely misfunctioning. There are some networking problems with downloading your profiles and everything, so hopefully they can fix this soon. One of the tips I can give you, and an experience from last year, don't try to work on your network folders. So if you have your projects and everything in your documents, that's actually on the network itself. If you try to run your tools on it, it will take a lot longer because it tries to synchronize with the network backend all the time. So take your folders and files, put them into your download folder, which is actually a local folder on your machine right now. And then once you're done at the end of when you're leaving, put them back in your network folder and let it sync back. And that will help you speed up the process of compiling, placement routing, and all kinds of stuff. And hopefully we'll get rid of some of the issues. I don't know what's exactly going on, so I will plan to go down there and talk to the staff and see if they can fix it or if they already have fixed it or not. A couple of more pointers. The logic analyzers that we are using is the Salia Logic 16. It has a really nice little feature that if you choose not to use all 16 channels, but only a subsection of the channels, and it can go a lot faster and you can sample a lot faster. You can actually go up to 100 megahertz on just 2 channels, and then I think it's about 25 megahertz if you use 8, and 16 megahertz if you use all 16 channels themselves. So sometimes if you need something to look at a signal that's a lot faster, try to reduce the number of channels, and that way it can go faster. Another tip that's always good for oscilloscopes, before you start using them, reset them to factory defaults. You never know what the state is of this oscilloscope when it comes up, who used it before, what settings they put in. If you're just completely lost, go to a reset to manufacturing defaults. That way you know the state of the scope. It's usually a pretty decent state, and from there you can go and actually dial in whatever you need to use. Try not to use the auto function. Oftentimes it doesn't really give you what you want. Oftentimes if you know what type of signal you're looking at, try to use the dials to go in the range that you think your signal should be and see what's actually there. Oftentimes you will find it that way much faster. Sometimes the auto function will just zoom into some of the noise that you have on your lines and you just don't understand what's really going on. A reminder, this Thursday there will not be a lecture in here. There will be a special session on PCB design taught by Inek Lee in MEB 2555. So that's not the digital lab, it's actually the ECE classroom, which is on the same floor, but it's in a different hallway that you can access it from. So it's like, if I'm not entirely mistaken, if this is the big layout there with the hallway here, there's a hallway here and another hallway up here. The digital lab is in this section of this block with an entrance door here and an exit door here. The classroom is over here, with an entrance door over here. Makes sense? So you have to go into the other hallway and enter it from there. Inek will demonstrate some of the capabilities of Altium Designer. He will go into details of some things that you should take care of when you do a layout and not, and what kind of things you should do, what you should avoid, what's the width of these different traces, what you should choose, what not, etc., etc. Homework, I extended it until tonight. Because apparently some people had issues with the files, had them stored on a network folder and couldn't access them anymore. So try to submit them as fast as you can today. I will start correcting them today, and as soon as I posted them, you can start with your next PCB layout itself. Another one of the things, do not expect an answer within 4 hours of a deadline. I mean, try to start homework, or at least start looking at it, figuring out, do I have everything, do I know everything, way before the deadline. Because usually at the deadline itself, it's crunch time, people are busy with other things, so try to get your information well before that. Same with the labs. Don't try to finish your labs in the last second. Like, try to do it, plan ahead with your assignments, making sure that you have all the information that you need. Couple of more announcements. Books. I mentioned it last time. The Definite Guide to the ARM Cortex-M3 is a pretty good book if you really want it. It's the one I would recommend. Try to use the 2nd edition, not the ones before. There are a couple of other books on embedded systems. Linux, for example, there's an Embedded Linux Primer. ARM Systems on Chip Architecture and ARM Assembly Language. They go more into details of specific topics, but the Definite Guide to the ARM Cortex-M3 is a good overview of what this course is all doing and basically putting all these ARM documents into text that's easily understandable. Mention it again, graduate students, we will make presentations. In the second part of the class, we will talk about that later, and your project should have a research component. Some people have account issues in the digital lab. I talked to Kate and what's actually going on. So if you want general documentation, go to www.kateutah.edu. There's FAQs and lots of information on what's going on. If you have password issues, go and use the user tool. You can actually reset your passwords on there. And if all else fails, contact them at APRS@encoding.edu. Okay? They are not handling access to the digital lab itself, though. In order to get access to the digital lab, you have to go during regular business hours into the digital lab or into the stock room, which is right next door. Talk to them and tell them that you need access to the digital lab, and they will give you a form that you can fill out, and they will give you access, hopefully within 24 hours. Sometimes takes a little bit longer when they just do everything on Fridays, for example. All right, next step, minute quiz. Let's see. All right, oh gosh. Head is minute quiz, tail, no minute quiz. Tail. Tail, no minute quiz. You guys are lucky because I also forgot my little flyer, so. All right, let's do it anyway. It won't count, but let's try to solve this exercise. It won't count, but just try to solve this on your own, all right? It would have been for more than a minute, by the way. See lots of blank stares trying to figure out what's actually going on here. Who tried to solve the equations for this for their LEDs on their boards and actually size the resistors appropriately? Some of you? Because I looked at some of the submissions and many of them just kept it at the 1K default value. So at 1K, the LED probably will barely light up. So how does this work? Who could have solved this? Yeah. Good part, actually. Okay, that's good. So how do you start? So first of all, I'm not telling you how much luminosity I really want, right? I tell you twice as much as you get at 5 milliamp hours. So if you actually look at this graph over here, this is the current divided by the current at 5 milliamp, or the luminosity divided by the luminosity at 5 milliamp, right? So twice as much luminosity would be up here. This is 1. This would be 2. So now the current that you get would be 15 milliamps. Right? So you need to have 15 milliamps going through this LED in order for it to light up twice as bright as it is at 5 milliamps. So far, so good? So what's the next step? Exactly. You need to find the voltage drop corresponding to the 15 milliamps. Right? So if you go here, this is the forward voltage, forward current milliamps. This is actually not 5, this is 15 here. Go down. So it would be 3.5 volt. Now what? 7.5? 6.5, yeah. So now we know we have 3.5 volts over the diode at 15 milliamps, right? So now we know over the resistor, we have 6.5, because over the total, we have 10 volts, right? So if we have 6.5 volts through the resistor, we know we want 15 milliamps. What do we get? About 400-ish, 433 ohms. Right. Any questions? Yes?
Isn't it more like 3.1, 3.2? Is that a lot?
Yes. You're right. Wait. No, it's 5.
That's 50, right? No,
It's 15. Oh.
Oh, it is 50.
It is 50. You're right.
So it should only be like
Good. Yes.
So it's more like
It would be down here somewhere.
Yeah.
Yes. You're absolutely correct. I'm sorry. It's a logarithmic scale. This is not 5, it's 50. It's up here, it's 100 milliamps. So what would we get? It's like 3 so this is 20, 15 would be here, about 3.1, 3.2-ish, something like that. Yes?
So on the intensity graph,
Yes.
what's the dashed lines?
The dashed lines, these?
Yeah, what is it?
Down here, it will probably not really light up anymore. So it's not entirely sure, it's just not bright enough. And up here, it might not be recommended to be used anymore. So that it gets too bright, too hot, and might melt down. But I would have to go and look at the data sheet exactly to see what's really going on. Yes?
I kind of had a hard time finding out what the rail voltage was going to be
Okay.
on the board. Is that something that's pretty defined?
Depends on what you hook up to it. Right? If you hook 5 volts up, stuff will start smoking because your MSP is only rated up to 3.6 volts. But so generally, the MSP, if you go and look at the data sheet, it will run anywhere from about 2.1 volts up to 3.6 volts. So it's really depending on what you provide to the whole board itself, since we don't have a regulator on the board. Most of the times, it's like 3 or 3.3 volts. So but it's up to you to decide. And you will also find out that with LEDs, it really doesn't matter that much what your resistors is. Plus minus 10, plus minus 20% is absolutely fine. The LED will still light up most of the time. Just sometimes a little less bright than others. Now the tricky part becomes when you have LEDs of different colors. Because there, if you want them to be shine about at the same brightness, you really have to change the resistor and adapt them to the different values. Or else you will have a blue LED that is really extremely bright and another LED that's just not bright at all. Okay, so let's keep going. Today we will repeat a lot of the things that we saw last time because many of these concepts are really important. So we had the major elements of the instruction set architecture last time, right? So we had, on one hand, all the registers. We had the memory map that we do operations on and get data in and out from. All of them are 32 bits. We talked a little bit about endianness, but we will look at that a little more today, what this really means. We had the status register that has a couple of different specific values and conditionals that we can execute code from. And of course, we have assembly code that now does operations on the registers to store and get data from, or to get information from the memory, from code, execution that is conditional on the different status registers, and links or labels that point into memory themselves to go and jump to or get data from. We talked last time about the branch instruction, and this time I bring it up again because I want to look at a little bit more about the encoding of these different things. We have the encoding of B that can jump plus minus 1 megabyte. We have other functions that can only go up to 128 bytes. Others go up to 16 megabytes, any kind of size, etc., etc. We talked last time about why this is the case. B instructions can only go that far because they are encoded in 16-bit. Other instructions are encoded in larger numbers, and that way they can actually have larger constants associated to them. And then those that can jump to anywhere, they are usually based on a register, where the jump address is actually stored in a register and not encoded in the instruction itself. So this is an example where we have the branch encoding. We have 4 different possibilities for just the B encoding. We have B with a condition in the label, and over here we have another B with a condition and the label. And actually, when you look at this encoding here, The difference is that this one here will never have a condition because there is no space in its opcode itself. While for this encoding here, we have a conditional execution, but then we can only have an immediate value of 8. So you have less amount of data that you can go and jump to. If you need bigger and more complicated encodings, we have the T3 encoding. Note the difference here again is those have B condition label. These are called B condition.w label. The W stands for wide. It basically tells the assembler that it should use a wide encoding for this particular function. There is also a .n instruction, which means the assembler should try to use a 16-bit encoding for the variable. We will see that later in some real code. So what are these conditions that we can have here? Well, we looked at them last time. There are a whole bunch of different conditions that act upon what's written in the status register itself. And I highly suggest you, if you look at your quick graph datasheet, you have all the encodings or all these little mnemonics in there. But what you don't have is this column here, which is actually telling you what it will do. I suggest you write this column in there by hand because sometimes when you're in the homework or especially in the midterm, you want to know, okay, what was this encoding again? And if you have it written there, helps you a lot, trust me. So with these different little mnemonics, you can make functions executable conditionally. So you can execute a function depending on what the status register does. One very helpful block that actually helps you with this is the if-then-else construct. So the ARM assembly has this really interesting ITT block. How it works is you write IT, and then you have an X, Y, Z, and a condition. And the X, Y, and Z can be either a T or an E. So the T stands for a then, and E stands for an else. So it can be an if-then, then-else-else. So when is this useful? Well, oftentimes if you program in C, you have something like this, right? Where you say, if R0 is equal to R1, then you want to execute this, or else you want to execute this. Now, instead of having to branch and jump around in your code, in ARM assembly, you can write this as compare R0 to R1, ITTEE equal. So this will now tell us that these instructions here are conditional. And more specifically, we'll have a then, else. So then, equal, else, not equal, else, not equal. And this encoding represents exactly what we have up here in C code. It's a neat little trick with if-thens that you can do in ARM assembly. We talked last time about instruction classes. We have the branching, jump around in your code to go and execute different things. So basically you write into the program counter to where the next address should come from. We have data processing, anything that you want to do with this data, with the register, so you can add, subtract, multiply, compare, no, not compare, OR, XOR, and stuff like that. So any operations that you do on registers. You have load and store instructions, so getting data from memory into registers or storing data from registers into memory. You have exceptions, talk about them later, and a couple of miscellaneous instructions. So for example, wait for interrupts, you have sealing instructions and other things. Addressing mode, just a quick repeat. We had that last time, offset addressing, where you have a base register and then the offset is taken from the base register, and that's actually the address that you're operating on. You have a pre-indexed addressing where the offset is actually applied to the register, and then that number is used for an instruction. Or you can use the post-indexed addressing where you're using and operating on the value inside the register, and once you're done, this offset will be applied to the register itself. So there's a difference between this one and this one, that one time you apply it before you do the instruction, and the other time you do it after the instruction itself. A couple of possibilities for this offset. You can have an immediate constant. In this case, #10 is a decimal 10 constant. You can have an index register sometimes, depending on the encoding, where the offset is stored in a register itself. Or you can even have a shifted index register. So you have a register, but before it gets used, it will be left shifted or right shifted in one direction or the other. Also from last time, just a reminder, there's a difference in when a function is updating the status register and when it is not. If it has an S at the end, it will update the status register. If it doesn't have an S, it will not update the status register. Any questions so far on the topics that we had last time? Yes?
The C at the end of, for example, add C means that it's conditional, okay? For example, add C.
Yes, you could have a conditional there, yes. But then it would not be a C, it would be an add NE or add eq or stuff like that, yes. Okay, so what does some real assembly look like? This is a code example where we took an assembly code, we put it into opcode, into objects, and then disassembled it, and this is what you get out of it. Do you guys recognize many of these functions, or could you look at this and tell approximately what's really a little bit going on here? So let's look at, yeah?
Does the assembly type have the actual register values?
Sorry, again,
Does
the quick ref?
not necessarily the quick ref, but does is there a map from the lines to the actual registry values?
Yes, there is. Let's see. Here, conditional, that's the encoding.
Okay.
So if you look at, for example, if you want an equal, the condition would be 000, or an NE would be 0001. The conditional is stored in here, in this instruction. So if it would be a 1101 and then 0000, and an immediate, it would be a branch equal instruction. We were talked about this. All right. So what's happening here? Well, the first instruction is a push R7LR. Anybody know what a push would do, or an idea of what a push would do? Store something, right? Push. You probably have heard of push and pop, right? C programming, that's when you put stuff onto the stack and away from the stack. That's exactly what this instruction is doing. It's pushing R7 and the link register onto the stack. We will talk about the stack a little bit later, but basically the stack is where the stack pointer is pointing to. Remember, in one of the variables, in one of the registers, the SP, the stack pointer will point somewhere into RAM, and that's your stack. And the push, all it will do is it will take these two registers and store them into the address of where the stack pointer is pointing to. So once we do a push, what happens here with sub SP16? Moves the stack pointer down. Then we add our 7SP0. What does that mean? It's a little bit odd, right?
You're adding 0 to the stack.
Yeah, you basically store the stack pointer in our 7. This is something, sometimes you will see code that's generated and you will be like, what? That doesn't make sense. We could have used a move. Most likely you could have used a move, but it's probably one of these constructs that just happens all the time. They just use an add for principle because sometimes they want to add a number in here. So you will see stuff like this all the time, especially when you're using non-optimized code. It's actually a lot worse. There's a lot of that code that's just sitting there that doesn't really do anything, but it's just there in the templates that they're using and they're not optimizing it, so all the templates are there. Even if they're not doing anything, they're still there.
With that push, what
Yes.
order do they get pushed to the stack?
I'm sorry?
What order do those registers get put into the
Good question. I would have to look at what the push instruction really does. I think it goes from low to high. Not entirely sure though. It could also go the other way around. And we will actually talk about the stack and push and pops in later sections, because there's a lot of things that actually happen automatically on the ARM. Remember when I talked about that the ISA can help the binary interface and function calls? This is one of these things that we will see in certain branch instruction. The microcontroller does actually a couple of pushes and pops for your, just automatically by executing a certain assembly instruction. this .n and .w that you can see sometimes here, so a .w and a .n down here, just helps the assembler to tell, I really want a 16-bit instruction, or I really want this to be encoded in a 32-bit instruction. That's all it does. Okay, endianness. Well, endianness is, you can think of it as a religious war since 286 years and counting. So it's basically started, or one of these things that was there in the historical inspiration of Gulliver's Travels, where you had the big Indian people and the little Indian people. One of them opened the egg from the pointy side, the other ones from the big side, so they were the big Indians and the little Indian people. So that's kind of like where this moniker comes from, where the name Big Indian, Little Indian comes from. It was also published in a satire on CS religious war in 1981 from Danny Cohen. It's a fun read if you want to look at it. And actually the conclusion really is, well, it really doesn't matter if you go Big Indian or Little Indian. Just do whatever you want to do. At the end, it's all the same. It's just bits and bytes in the text itself. So what does it really mean? Well, it's how bits and bytes are stored in your memory itself. And if you either go least significant bit first to most significant bit, or if you go from most significant bit to least significant bit. So how does the encoding work? In Little Endian, assume you have two unsigned integer 8s. So these are 1 byte variables, integers, unsigned, and a 16 one and a 32-bit integer. They're defined as a 1, 2, 255, and 1, 2, 3, 4, 5, 6, 7, 8. This makes it easy to actually see what's happening in memory. This will be stored in memory, address 0 as a 1, a 2, 255 is actually as a 16-bit encoded as 00FF. Since we are Little Endian, we have FF00. So it's least significant bit first, most significant bit later in memory. And then stored 1, 2, 3, 4, 5, 6, 7, 8 as 7, 8, 5, 6, 3, 4, 1, 2. Big Endian is exactly the other way around, where we have the 1, the 2, 00FF is just 00FF. And then 1, 2, 3, 4 would be in memory stored like 1, 2, 3, 4, 5, 6, 7, 8, 9. Easier to read in memory than Little Endian, but at the end it really doesn't make that big of a difference. You really get used to flipping around the bits very quickly. ARM Cortex-M3s are by default Little Endian, but many ARM systems you can actually switch at startup to be Big Endian. So you can actually flip them around. There are also a couple of instructions in ARM assembly, more specifically their REV and REV16, which will change a Little Endian to a Big Endian number. Sometimes very useful if you go and communicate over a network, and if you have to talk to somebody that's not a Little Endian like you can use their ref function to actually flip it around into your instruction codes. So we looked at this last time a little bit, but I want to just show you again how opcodes are actually generated. Let's take these two instructions. We have a move of R0, 10 and a move of R0, 1, R1, 0. If you look at the encoding, it's a very simple encoding. We would see a 0, 0, 1. That's our move S instruction. 0, 0. We have the destination register and an immediate 8. Right? So the one up here gets encoded into 0, 0, 1, 0, 0, 0, 0, 0. 0, 0, 0, 0, 1, 1, 0, 0, 1. Right. If you look down here, you can actually see exactly the beginning code. The register will be R0, so that's a 0. And then 10 is encoded down here as 0A in hexadecimal. If you look at this one here, the difference is that in the destination register, you now have register 1. And the immediate value is 0. So taking these two things and converting them into Little Endian will actually end up like this in memory, where we have the lower one, least significant bit first, so 0A, and then 2, 0 gets stored here. And this encoded as 0, 0 back here. And this one here is a 2, 1 gets stored in the second. Any questions to encodings? No? All right. Then let's go and see what happens at a reset or at the boot up of your microcontroller. Because there's a lot of stuff happening there. A lot of it has to do with powering, like how to power up the system, how to take things out of reset, etc., how to make sure that the power is all good to your system. And then once the microcontroller actually starts up, the Cortex-M3 will do two very important things. The first one is it will read the stack pointer from memory address 0, and then read the next memory address, so 0x4, and jump and set the PC or the program counter to that particular value. So at location 0, it will store whatever is written in there into the stack pointer so that we know where the stack is sitting in our RAM. And the second address is it will go to this address, read it out, and will put the program counter to that value to start execution at the address stored in this memory location. The interesting part about this is that 004 is actually where the vector table starts. So the vector table is where interrupts will go to, and they will look for different specific functions. We will talk about all of this later, but you can see that at address 4 is where the reset vector sits. So whenever you hit a reset or want to execute a reset, all you have to do is go read this memory location and then jump to that address, and you will basically reset the software of your microcontroller. Fairly simple to do. And then after the reset, execution begins. So how it's done in your assembly code, you set the stack top to a certain memory location. You say that the global is at _start, and then you define two words in the very beginning, a start, the stack top, and the start. So this one here is actually a label to the memory location wherever this function is sitting in assembly. And the beginning part here is just this address. And then the linker will actually make sure that this is written into the right location in your application. So the first two words in your application will be the stack top and the first jump address of where execution starts in memory. How does this happen? Well, that's what we're looking at now, the assembly tool flow. So how do we go from your assembly code down into the binary code that actually can get uploaded in your microcontroller? Because there are a couple of different steps that are actually happening before this is possible. First, you have an assembly file. You use the assembler to make this into an object file. You then use a linker with a possible linker script to tell where this now all belongs to in an executable file. Now, the problem is the executable file is just kind of like a bag with all the information inside of it. And from there, you then use a different tool, object copy, to make this into a binary program file. This is then a file that's used for certain applications to program your microcontroller. So you can see it's a fairly long chain until you get to your binary that you can actually upload in there. And each and every step does something very specific, and we will look at them now in details. There are a lot of different tools that you might already be familiar with from the GNU toolchain. The big difference is now, because we're using a cross-compiler toolchain, you're adding ARM non-EABI as a prefix to them. So if you have used GCC before, you now just use the ARM non-EABI GCC. If you used the LD, the linker before, you just now use ARM non-EABI LD, etc., etc. The key here is that these tools are cross-compiling. So they're taking a code that you're writing on, for example, an x86 machine and compile it for an ARM platform. In our case, this will be an ARM platform that's adherent to the EABI binary interface, which we will look at later on. A simple hard-coded make script that could generate your assembly file and actually does all these steps in one, and you will do that next week in lab number 2. We first execute the assembler. We tell it that we have a Cortex-M3, thumb code, our assembly script, and we want to generate an object file. Right? That's the first step. We now have an object file. Next, we use the linker. This time, we don't use a linker script, but we give it a couple of parameters that we will look at. We give it the object file, and we generate a .out file. We next can use the object copy to take this out file and generate a binary file. Or we can take that same output file, use an object dump, and actually disassemble it to go all the way back and actually see, did the assembler do the right part, and how did he actually optimize, or what did he do with our assembly file itself. So what kind of information does this assembler provide? Well, we looked at it before. We have this, the assembler file up here. And if we disassemble it at the very end, we can see that it goes from something like this, which we have seen before, to something slightly different. What can you see as the big differences between the two files? Program counters? Sorry? Exactly. The labels have all disappeared, right? And you write assembly, you just write everything with like start labels, loop labels, dead loops. And what the whole toolchain does now is actually mapping this to actual physical memory locations on your microcontroller, right? So it replaced the start with 0, 0, which is what we told it before, right? That's address 0 is where we start. It then has the first two words. Now you can actually really see that the stack pointer gets read from here. Then the first jump address at 9. If you can look at here, down here, address 8 is actually our start location. Do you guys remember why this says 9, even though the memory address is 8? I mentioned it briefly last time. Sorry?
You're not offsetting for your instruction. No.
It's not an offset for instruction, no.
You want to start at the beginning of the next word?
Nope.
Because it's the little ending and only two 16-bit words.
Almost. It's actually telling the microcontroller that whatever is at this location is actually a thumb instruction, not an ARM instruction. So if this were 8 in here, it would mean that wherever you jump to is an ARM instruction. And if you ever try to do this on your Cortex-M3, you will get a hard fault, because the Cortex-M3 cannot execute ARM instructions. And we will see when this is actually added a +1 or when it's not. And sometimes you don't have to do it because some of the jump functions can actually not switch your execution code, but others you have to actually add +1 to the memory location, or else you will get a hard fault. Sometimes very confusing to figure out what's going on. All right. So what are the elements of a real assembly code? We looked at that before, and here it's just spelled out. We have the first one that equates the stack top symbol to this memory location. This is kind of like a constant variable that you can set in your assembly codes. The next one tells the assembler that this is the text section that we want to write. We will talk about sections in a few slides. We want to use the unified syntax. So this is which ARM language that we are actually using in your assembly code. We have telling it that we are using the ARM thumb ISA in this particular object file that we want to compile. We tell it where the global start address is. We tell that start is a function itself. So we tell this to the assembler so we can do certain things automatically that we don't write in our code. And then the rest we have talked about. So just as a quick exercise, how often do we execute the loop? Teams of 2 get together, try to solve this quick. Was an answer? 10? Okay, 10 is right. So what happens? We store in R0 and our 10 in R0, 0 in R1, right? Then we add to R0, R1. We subtract 1 from R0, so we have 10, this is now 9. We branch, 8, branch, branch, branch until this is 1. Once R0 is 1, we subtract 1. This loop will not be executed, and we are sitting down here in our dead loop. Okay. Let's have a look at this quick ARM assembly line here. We have the ARM non-ABI assembler that we are using to get whatever your assembly file is into an object file. What do we tell the assembler? Well, we tell him that our CPU type is a Cortex M3 and that the assembly that we are using is mthumb. We tell it the actual specific assembly file that we want to assemble and the object file we want to store the output into. Now, if something is wrong in your assembly file, this will throw errors and will tell you all kinds of stuff that you shouldn't have done or have to fix. How can you look at this object file again? Well, there's a small little application that's called readelf that you can actually go and look at the format in there. It will spit out all kinds of different information. So it will show you what the headers are, what the program headers are, what the different sections are, symbol tables, file attributes, etc., etc. One of these outputs looks like this. I'm actually not entirely sure if the Windows machine will have readelf on them, but if not, go to a Linux machine. Most of them have readelf installed. This particular case, this example.o file has 9 different sections. It has an empty section at the beginning, which has 0 size. Then we have a text section, we have a data section, the BSS section, and a couple of other tables and files that are sections in the elf instruction itself. So now what can we do with this object file? Well, we can give it to a linker. And the linker will now replace all these different tags and symbols with the right memory locations. So the linker has a couple of different parameters that you can give it that you can also store in a linker script. So in this case, they're spelled out specifically. So what we tell it that the text section that we have seen over here, the .text section, whatever is written in there, should be put at address 0. And we want the BSS section to start at address 2000. Any idea of what the address 0 means and the address 2000 means? Could they be any number? Could I put in here 0, for example, 2? And what would happen with that? Any ideas so far?
Generate the out file that would try and put your starting spot at the very beginning, so you never get out of there.
Yeah, so horrible things would happen, yes. So the linker script will probably oblige and actually do this for you. But the problem is that in reality, your physical hardware will probably not accept this file. Or it would just not execute, or nothing would happen at all. So the 2000 here is actually very specific for the ARM Cortex that we are using. At 2000 is where the memory RAM sits. So that's where the RAM memory sits, where you can store in variables, have very quick access to. It's very, very fast. While address 0, remember, that's where we have to store our first initial stack pointer and the jump address into. And that's usually where the code is sitting. So the text section is where all the program code is. So that you write at address 0 and continue from there on. So the linker has a really important job here. It takes different object files and actually places them in the right memory locations inside of your architecture. Yes?
So does the RAM count up or does it count down?
Up. This is what a linker script looks like. So instead of giving all the parameters to the linker on the command line, which can sometimes be very tedious, you write a linker script. This is a very simple linker script. So what you tell it in here is you have a memory location, specifically RAM. RAM is read, write, and executable. The origin is at 2000, and we have 64K of it. And now, down here in the sections table, you can now tell where you want to put each section of your code. So in this case, we want the .text section. We want it aligned to a 4-byte interface. So this is a one word. It has to be word aligned. And it then selects all the different text sections that we have. It sets a label to the end of where text stops. And it will put this into the RAM memory location. As I said, this is an extremely simple one. We will look at more complicated ones later on and also in lab, where you can put stuff not just into RAM, but also into ROM. And usually into ROM, you only store stuff that's constant, so either executable or readable, but usually not modifiable, because modifying ROM is either impossible to do if it's burnt in, or if it's flash memory, you have to use specific functions to actually go and modify your flash. So usually, ROM is only read and executable, while RAM is read, write, and executable. So what does then an executable image contain? So this is the image that you get out from a linker script. Well, it certainly still has the .text section. This is the executable code, and has also the initial reset vector in it. You then often have a .data segment or a RO data section. So RO data is usually only read-only data, while .data section sometimes can be writable. This is the static part. It's initialized variables. So whenever you have a variable in your C code, that will go into the data section because it is data that has to be read and has to be initialized in the beginning of the startup of your application. Then the .bss segment is basically all the variables that you define that get used that are not initialized. So what happens with a variable in C code if you don't initialize it? Who knows? If you have a variable that you have not initialized and you start using it without assigning anything to it. Yes?
Contains whatever's in that location, right?
Yes. So it's not guaranteed that an uninitialized variable is actually 0. It's not guaranteed. Now, many systems try to do it. So because these variables sit all in the BSS, what oftentimes happens is that your OS goes into that section in the very beginning of the startup of your application and just writes zeros all over the place, making sure that everything is 0, but it's not guaranteed that this really happens.
So I'd say that things like int variable name does not have an assembly equivalent. It just is in your C code, not in assembly. Well, it depends on
Yes.
the
It does depend. Sometimes that's when stuff becomes complicated. So the compiler then decides, do I really need a location somewhere or not? So for example, global variables that you're using, even if they're int something, and they will most likely be a 32-bit integer or assigned to a 32-bit integer, they will sit somewhere in memory. So it will create a BSS entry for it, and then later on it will just use that particular memory location wherever you use this variable. So you will see that all in your code next week. The key to this is also that it does not include a heap or a stack, because that's sitting usually in RAM, and you have to make sure that whatever is in the BSS section does not collide with your stack itself. So then how do you read one of these files? Once you went through the linker, you get a .out file. Well, it's exactly the same thing as before. You can just use the read hex and read elf, and you will get the output of an out file. So then what really changed? Well, if you look at it, the same application that we had before, if we first went from the .s file to the .o file, we had 9 sections, if you remember. Now, all of a sudden, we only have 6 sections left. Anybody know why? Why do we only have 6 sections left? What happened to the other sections? There are 3 sections that disappeared. They were not important. Right? The linker now sees that, oh, these sections are not even used. And in the linker script, we didn't link them back into our sections. So they will not be put into the .out file anymore. Any questions? So here comes now the cool part. If you actually look at all these different files, you can actually start seeing the things that you wrote. And you now start to understand how this stuff is put into these binary files. And at the end, you really can read out, again, what your assembly instructions are. That's basically what a disassembler does, right? So if you use the read elf with a -x, we actually get a hex dump, which just means it's translating whatever is in binary written in there into as a hex output. And what we can see is, if you use the hex dump, first initial part is the .text section. Interestingly, recognize this number here? Stack pointer. But yes, it's in little endian. It's 20000800. Right? Goes from least significant to most significant bit. The next thing here, we have seen this number before, right? It tells us that it's a thumb instruction because it's a 9 and not an 8, but this is the reset vector jump address, right? Like it's the start of where we start off at memory address 8. And that's here. And now if you want to go into details, you could start decoding this using the ARM and actually figure out what all the different opcodes are and what they represent as assembly instructions. And that's really what all a disassembler does. It just has a huge table of all the codes that are possible, and it will do the reverse of what's written in this file. Not too hard, a little bit laborious, but not too hard for an application to do. So what's the raw data really looking like? Well, if you do a hex dump on the example 1.out, you will first see a big block of stuff that has what's called the ELF magic number. If you have ever used a Linux system, if you type and then the file name, it will try to identify what this file is. Many of file types actually have what's called a magic number, so it will always have the same number here at the top telling you this is an ELF file. And then down here, you can see the same stuff again. Do you notice something? Slightly different than from what we have seen before, right? It's now in half words, little endian. Instead of byte-wise, it's now half words. So we have 2000 and then 0800. Sometimes very confusing to figure out in little endian what's what. Sometimes it's really on per bytes. Sometimes it's on half words. So you have to be careful of what you're looking at. So what's the purpose of this executable file? Well, it basically serves as a container before you really put it into applications that can program your microcontrollers. They keep different segments partitioned with different access rights. They serve as an image for operating systems. So if you have ever upgraded your Linux router, for example, or like your Wi-Fi routers, you usually get one of these images, and then you take this image and program it into your microcontrollers. They oftentimes have debugging information, so your IDE can actually find out what's written where and actually find the link back into your C code. That's all stored in this executable file. So how useful are these executable files? Why do we even have them? Why not just use the binary files only? Any idea? What's an advantage of having this huge container with all kinds of information in it, when all you really need is the binary file, right, to program your microcontrollers? Because that's really what's getting uploaded into the flash memory, where everything starts. Yes. These executable files are really important for debugging, because without them, you don't really know what's going on or what the different C instructions mean. So the executable file is really the link between your C code, your assembly code, your source files, and what's written in your binary file later on. So then, what does a binary file have in it? So once you send it through object dump, you can look at it again, and no big surprise really, right? We have the stack pointer, the first jump address, and after that comes your program. It's going to be sitting in code and gets executed as you tell the machine to do. If you want to, you can now, since you understand opcodes, you can actually use hex edit and go and edit this binary file. And if you have ever, back in the day, I'm not sure how computer games work these days still, but back in the day you could oftentimes just go and edit your .exe files in Windows or Linux, and you can go and screw around with your lives and have tell it that, well, actually you have 100 lives to start off and not just one if you knew where it is and stuff like that. So that's exactly what's happening here, right? This is the code that's going to get written into the flash memory. And if you want, you can now go and edit this code and do something else. This is oftentimes how people crack phones. They go and look at the binary files. They actually go and read these binary files, disassemble them, and then find out which function they have to go and change to actually circumvent certain protections. By understanding what's going on in the binary files, you can figure it out. So oftentimes these binary formats are not very useful, unfortunately. Oftentimes programs don't use them. There are two other formats that are way more common. That's the Intel hex format, or iHex, or the other one is a Motorola S records. Fortunately, object dump can produce both of them, so you can tell it to do a binary file, an iHex file, or an S record file. It's just they all have more or less the same content in them, except that some of them are ASCII, others are pure binary files. So for example, if you generate a hex file, the content looks something like this with a different notation. If you use an SREC file, a Motorola file, the stream is just encoded differently. More or less the same information, just in ASCII and in different formats. All right, we have about 20 more minutes. So we now looked at the C assembly flow, or how we go from assembly into our binary files. So let's go one step further and see what happens if you have C, right? So we have seen this one here, where We have the assembly file, use the assembler, object file, linker script, generates the executable. This is the big container with all the information that you really want for debugging and programming, etc., etc. And then from here, you can use object copy to generate binary files or hex files or the other type of ASCII files that then your tool will use to program into your microcontroller. Or you can go all the way back to here and actually disassemble the whole thing. If we add C into the picture, it gets more complicated. And now we add a tool that's called GCC that does a lot of magic for you. Instead of having the linker in here, you use GCC. And GCC takes C files, takes object files that were generated with an assembler, or it can also use libraries that were written as objects before, takes all of them together using a linker script, invokes the linker on the side, and generates your executable image. So GCC is really this magic box that does most of the things for you. And one last thing, if you really need to add assembly into your C code, there's a small little trick that you can use with the statement __ASM that will execute assembly code. It's a little bit tricky on how the notation is, because imagine that the problem now is you have assembly code and C code. You have them to work together. So you somehow have to tell the assembler what your input is and what do you get out from your assembly code. Because in assembly, you don't have variables, really. You have registers. But in C code, you have now variables. But you don't really know where all these variables are stored at which point in time. So how to do this is with this notation down here, where you can say that you have the different output variables that's stored in a register, you have an input variable that's stored in a register, and you have the cobbler list of R3, which is basically the register. You tell it which registers it can use that don't have to mean anything after this execution anymore. So it can use the R3 as a throwaway later on. So what happens is output, input are two variables that we have here. They're unsigned integers, input and output. And it will take them, store them in a register, and it will output it. It will take input, store it in a register, and will output that register back into the output itself. So that way your assembler actually knows and can now decide which registers it really wants to use at the position of %0 and %1, optimize this for the current execution of the code itself. So if you want to actually try this out, you can write this into a C file. You can use GCC to compile it down, and you can see there's no assembler in here. So GCC actually knows how to deal with the assembly code. And you can then use QEMU, which is an emulator for ARM. Especially works fairly easily on Linux. You just can get it and install it. And then you tell QEMU what CPU you're running, and it will actually output stuff for you. And I think that's it. Yep. Any questions so far?